Hi, and welcome to our next session here in our chapter on regularization. So here I will discuss the important correspondence between weight decay, especially how this is usually framed and called in the context of neural networks, and L2 penalties. Okay, we'll do that in the context of a simple gradient descent, and also discuss how weight decay or L2 regularization then changes the optimization trajectory during optimization. Good. So let's write down again the objective function for RRM. And I will use now specifically L2 regularization here with a control parameter of lambda divided by 2. And here the first part of the regularized objective is simply our good old empirical risk. And I now want to consider what happens if I optimize that thing by gradient descent. So if I want to apply gradient descent, I guess I better compute the gradient of that thing, the negative gradient, because we know the negative gradient points into the direction of strongest decrease of a function. Gradient itself points into the direction of steepest ascent. So for steepest descent, we have to do a 180 and negate the gradient. So what's the gradient nabla theta of my regularized risk? Well, that thing here is a sum. Gradient is a linear operator, so we can push the nabla inside of that sum. So for the empirical risk, I haven't made any specific assumptions here how this should look like. So I'll just write nabla of Rm. But this thing here, I can easily compute the gradient of, right? So the gradient of that thing is simply going to be lambda times theta. You can also see where I've put the 2 here, so that this nicely cancels out and the resulting formula is a little bit simpler. So if that's the gradient, we can now write down the update formula for gradient descent, which is, I don't know, also pretty easy. So we write down that our new parameter estimate, lambda theta nu, is the old one minus a step size alpha times the gradient. So we simply copy in what we have learned regarding the gradient before. I don't mean in the sense of machine learning, but what we have learned as students about the shape of the structure of the gradient. So we just copy in our result from before in here. And now we just rewrite this ever so slightly. Okay, we just distribute terms a little bit because there's also a lambda old in here, and we combine that with that guy, which gives us, why am I always saying lambda? It's theta, okay? So it's theta old now times 1 minus alpha times lambda minus alpha times Rm. And after we have done that, and after we've done this minimal rewriting and distribution of terms, reorganization of terms, now we stop and we look at that. So what's the structure of that formula? Well, this second term here, this is simply the normal gradient descent step we would perform if we would do gradient descent on the unregularized empirical risk objective. And we do that gradient step, of course, based on the position of theta old. But before we apply that, we now do one extra step. If we have a penalty in there, if we have a rich penalty in there, and this results in us multiplying theta old with 1 minus alpha times lambda. And now consider the very usual case that alpha and lambda are not very large, specifically that they are smaller than 1, then 1 minus alpha times lambda is also going to be some value between 0 and 1. So I don't know, maybe the result of that thing here is 0.9, okay? So what happens now in gradient descent? So you take your theta old, the position where you currently are, you multiply everything, every component by 0.9, consequently shrinking their magnitude a little bit, and then doing the normal gradient descent step on the unregularized objective. And this is exactly what happens then in regularized risk minimization with L2. And this is why we call that weight decay, because we do a decaying weight step. We multiply weights by some value, I don't know, between 0 and 1, and then doing a normal gradient descent step. Okay? And if you ever look into some I don't know, neural network or deep learning software, this is often how it is called. Sometimes it might be called using rich regularization, L2 regularization, but very often it's called weight decay. And then very often you are asked to set this combined parameter here. Yeah, so this decay parameter. Yeah, whether you want to set it to 0.9 or 0.9 or 0.5 or something like that. But from this slide here, you should have now understood that this is nothing more than L2 regularization in disguise. So again, another instance in machine learning where confusingly we use 3 different terms for the same thing. So yeah, until now it's 2. Yeah, well, I guess 3 if we, well, I guess it's 3 because we could also call it using a Gaussian prior on our weights. I've visualized this here so you can get a better feeling for that. So here's some objective function, some unregularized objective I'm optimizing. So this might be my ERM objective function, I don't know, some quadratic form or whatever. And I'm now doing gradient descent. I'm starting in the origin, and I'm now moving across my contour lines now to that point here through gradient descent. So roughly moving orthogonal to my contour lines. And on the left-hand side, this is without weight decay. And on the right-hand side, you can see what happens under weight decay. So in each step, I'm getting pulled back a little bit. Yeah, I'm getting pulled back a little bit to the origin in each step. So it takes me longer time to arrive at the optimum. And if I early stop that, yeah, I will be located much further away from the optimum. So in order to show this a little bit better, I've also tried out different lambda values here. So on the left-hand side, this is a small value for lambda, and here's a larger one. And especially here on the right-hand side, you can now see this stronger pulling back to the origin that happens in weight decay. So to make this very clear, so we've seen this correspondence before. So this is how my weight decay looks like, right? So I have now fixed my step size alpha, but I've varied this thing here, and yeah, the resulting value would be my weight decay value. Short caveat, so there's a certain history for weight decay and also sometimes a certain amount of confusion going on. So if you look into what I've discussed here, constructs this equivalence of weight decay and L2 regularization, but that kind of only holds in the context of gradient descent or stochastic gradient descent if you want to. On the other hand, I haven't also claimed much more. First comment, first caveat, so if you look into this original paper by Hansen and Pratt, which is now fairly old, from 1988, they actually define weight decay decoupled from gradient descent update steps. So they give a slightly different formula here with a lambda without an alpha, okay? So of course I can rewrite that to my form by just setting lambda dash to alpha times lambda. The point is, if you now begin to talk about an optimal lambda dash, so an optimal weight decay setting, then this L2 penalty is tightly coupled to your step size, okay? So there's a correspondence between them and vice versa. So all of these 3 values here, they're in correspondence to each other. If you look into a more modern paper here by Loshilov and Hutter, they actually show that there's no equivalence between L2 and weight decay in the context of adaptive methods like the Adam optimizer. And these are actually the optimizers we are usually using in practice when we optimize things like neural networks, right? So while in many cases SGD and L2 works quite well, if you do Adam and L2, yeah, which might be a more interesting combination, then this usually underperforms because of this non-equivalence, yeah, to weight decay. And they actually propose a certain variant of Adam, which again decouples weight decay from gradient updates. So this is called Adam W, and it actually increases performance over Adam and naive L2 regularization. I'll not go into the details here, just wanted to mention that so you understand that if you're more interested in that, or so you're at least aware of that thing. If you're more interested in the details, I highly encourage you to look into this paper. Probably also a good idea maybe to, if only for historical reasons, just to see where everything started, to look into the original paper of Hansen and Pratt here. Okay, that concludes this brief session here. I hope you enjoyed this and you learned something interesting. See you in the next one.